Hey everybody, welcome to Embedded ARM Dev. In this video, we're going to explore the ELF section header in more detail. If you haven't already done so, I recommend you check out my other videos that introduce the Linux ELF files and the ELF file header, which will be helpful for understanding the material in this video. The goal of this video is to describe the structure of the ELF section header. First, we'll take a look at the elf.h to examine the structures and definitions that describe the section header. Then we'll cross-compile a simple program so that we can examine its section headers. We'll use readelf to get a readable output of the section headers. We'll also examine the section header in the compiled binary, which will be in the hex code. We'll use all of this information to walk through each field and examine it. Alright, so the first thing I want to show you is the section header struct, which is defined in the elf.h file. If you want to know how you can find this file, look at the first video in this series, Introduction to ELF Files. I went over how to find it in that video. So I'm just going to scroll down here to where I know the struct definition is. So right here we have the struct definition for the 32-bit section header, and then this is the struct definition for the 64-bit header. I know that this binary that we're going to be doing is a 32-bit header, so we're just going to use this struct right here. So we'll actually be referencing this struct throughout the rest of this video. The next thing I want to show you is the binary that we're going to be using. So it's just called hello.c. And it's just a very simple hello world. What I'm going to do is go ahead and compile it using the ARM cross compiler. I'll just call it hello and call it on that so we can see it there. If I call file on it, we can see it's a 32-bit LSB executable for ARM. Alright. So the next thing I want to do is show you the program header output for this binary. So again, this was the second video in the series of this series. I went over the program header. So if you want to get more detail into that, you can go to that video. So we're just gonna call that on this. So this will have some useful information for us as we go through and look at the sections. So we'll definitely be looking at that through the rest of the video. And then the last thing I want to show you is how to dump the section headers themselves. Capital S, okay. So these are all the sections right here that are inside this binary. And we are going to examine primarily the text section, okay. This is the information that readelf gives us, and we're going to actually see this information as we examine each field in the struct for the text section. Okay, so here we've got the ELF section header structure, the 32-bit one. So this is what I just showed you in the ELF file. You can see here that I've got the byte offset for each of these fields. So this is the byte offset inside the struct where the field starts. And it's also worth noting that all of these fields, the word, the address, and the offset, are all 32 bits each. So each one of these fields is 4 bytes in length. So this is the output of the file header using readelf. I covered the file header in great detail in previous videos, so make sure to check that out if you're not familiar with the file header. So there's a few things in this file header that will be useful when analyzing the section headers. So the first thing to notice is this tells us the start of the section header, so that's 7,120 bytes into the file, and 7120 decimal is 1 Bravo Delta 0 in hex. So this is telling us the section headers right here. This is telling us the offset in the file where these section headers start. Now remember, each one of these section headers describes one of these sections here in the rest of the binary file. And so here we have the size of the section headers. So each one of these section headers is 40 bytes. And note that this is just a section header, so the sections themselves will vary in length, but the size of each section header is 40 bytes. And finally here we have another important piece of information. So this tells us the index for the section that contains all of the strings for the section names. So the section header at index 27 describes the section that contains all the string names for all of the sections. So here we have the output from readelf showing some of the section headers, and we're going to examine the text section. The text section contains all of the executable code in the binary. So all this data here is contained in the information inside the section header, which we'll examine in detail. So down here we have the section index 27. This is the section header string table. You can see here, section header string table. This section is a table of null terminated strings of all the names of the sections. This section header string table contains all of these strings right here. These are the section names. So all of these strings are located inside this table. So one thing to note here in the offset column, that this particular section starts at address 1 alpha Charlie 4 in hex. So this particular information is something we could get out of the section header, but we're going to look at the section header for text. So I just wanted to point that out because that'll become useful here in a little bit. One other thing I forgot to mention is this column here is the section number. So this is the section number or the section index number, and so the text section is index number 13. All right, here, so what we're trying to do here is calculate the location of the section header for the text section. So this is not the location of the text section itself, it's the location of the section header which describes the text section. So if you remember from the file header output that the section header started 7,120 bytes into the file, which corresponds to hex 1 Bravo Delta 0. And again, from the section output of readelf, the index of the text section was section number 13, and the size of the section headers was 40 bytes. So if we take 13 times 40 bytes, we get 520 bytes. So the offset of the text section header is 520 bytes from the beginning of the section headers. So 520 bytes is 0208 in hex. So if we add these two numbers, we get 1 delta delta 8. And this location is the start of the section header for the text section, or index number 13 specifically. So I've got this right here. We've got 1 delta delta 0. And I've got 40 bytes highlighted here. So everything that's highlighted here is part of the section header for the text section. All right, so let's take a look at the first field. The first field is the section header name. And the section header name is just a byte index into the section header string table that contains the string name of this section. This is the binary output right here for the section header. So we can see, now remember this is a little endian, so it goes right to left. So we have a value of hex 92. And if you remember from earlier when I dumped the section headers, I noted that the section header string table started at address 1 alpha Charlie 4. So if we just go at an offset of 92 into this table right here, so we just take the table plus the offset, we get 1 Bravo 56. So coming down here, we have the hex for this binary. And if we go to the address 1 Bravo 506, which I've highlighted here, you can see that we have the ASCII for .text, which is the name of this section. The next field is the section type. This tells us which type of section this is. So in the hex editor right here, we see that we have a value of 1. And the 0x1 corresponds with section header type of program bits. So if you look at the legal values for the section header type, which this comes from readelf-h, we can see here that 1 corresponds with program bits, and that means that this is program data. So program data is just literally anything that it's used by the program itself. Some of the commons one you'll see sim tab for symbol tables. You'll see relocation entries if it's a relocatable file. And sometimes you'll see hash. Dynamic is if you got any dynamic linking, if you're linking into shared libraries, stuff like that, you'll see those in here. So you'll see a lot of these throughout. And so one thing that I found on the internet is this link right here, and we're going to take a look at that one real quick because it has a little bit more information about these fields. Okay, so here I've gone to this web page that was linked inside the slide earlier. And this is just a really good resource that I found for various Unix-related, Linux-related things. And the one we're going to look at right here is the TIS portable format specification. So I'm just going to pop that open. And so we want to skip down here to sections. And we're going to take a look at... Okay, so here, this is everything that we're covering in the video. So this is the struct. These are the different field names. so you can get more information about these fields than what I have here. And these are the section types that I'm showing you. Okay, so right here, this is the page that I want to show you. So this gives you more information about the different section types. So if you see one in your binary and you're not sure what it does or you're curious about it, this is one resource that you can try to look at to see if it gives you some information about this section. So here are the program bits. This tells us the section holds information defined by the program whose format and meaning are determined solely by the program. So we'll be looking at this throughout the rest of this video too when it becomes useful. Okay, so the next field is the section header flags. The section header flags are bit masked flags that describe various attributes. And remember, the word is a 32-bit, so that means we could have up to 32 flags inside this 32-bit number. So if you look over here at the legal values for the sh flags, again, this is from the elf.h file. What you can see here is this is basically a 1 shifted left this number of times. And so what that really corresponds to is this number on the right means this bit corresponds with that flag. So bit 0 corresponds with shf right, bit 1 corresponds with shf alloc, etc., etc. Okay. So looking at the output from the binary file, we can see that for this field we have a value of hex 06. Okay, and hex 06 in binary is 0110. So what that means is, so remember, this is bit 0, this is bit 1, this is bit 2. So we have bit 1 and bit 2 are set in this particular flag. So if we look right here, we see bit 1 is shf alloc and bit 2 is exec instructions. So what this tells us, this one's really important. So the alloc means that this section gets loaded into memory when the program runs. Not every section will get loaded into memory when the program runs, but this one, if this flag is set, then it does get loaded into memory. And then this one tells us that this is executable. So this obviously tells us this is actual code. So if that bit is set, then this particular section is executable code. And those are primarily, those three right there are the most common ones that you'll see. Okay, so the next field is the section header address or section header virtual address at execution. So this is the location in memory that this section will get loaded to if it gets loaded. If the field is all zeros, then this section does not get loaded into memory. So here I have the field highlighted, and so what we have is a value of 0103 0 Charlie. So that means this particular section will get loaded to 1030 Charlie in RAM. This particular section right here, which is right here, this text section, this would be 1030 Charlie inside RAM is where this would be located. So the next field is the section header offset. So this is the file offset where this section is located. So the number of bytes into the file where the section itself can be found. The field's highlighted here so we can see that we have 030 Charlie. So that means that the text section can be found hex 30 Charlie bytes into the file. So right here I've got the binary in the hexadecimal and the hex editor. And remember that, okay, so this corresponds with 030 Charlie is this address right here. So remember again, this is little Indian, so it goes from right to left. So the instruction, the first 4 bytes of the text section are echo 3 alpha 0 bravo 000. So down here, what I have is this is the disassembly. So this is assembly code. So I disassembled this binary and looked at the address where the text section starts. If you remember from the previous slide, this 1030 Charlie, this is where it expects to be loaded in RAM. So it's exactly 10000 bytes greater than the file offset. Okay. So what you're seeing here is actually this section header virtual address in this particular thing right here. In here, this is the file offset. Okay. So that's the difference. This is the file offset, and this is where it thinks it'll be in memory. So if we see here, these instructions right here, E3 alpha 0 bravo 000 is exactly what we have right here. Okay, in case you're curious, that just moves a 0 into the frame pointer. And if you don't know assembly, that's fine. In case you're curious also, this is the command. You use object dump and the D switch on the binary, and then you output it to some file that you want to name. It can be anything. Or if you don't use this, it'll just output to your standard out. So if you do it in the terminal, just dump it to the terminal. If you use the D, it only dumps the executable. If you use the capital D, it dumps everything, the entire file. It tries to disassemble everything. So depending on what you want. So the next section is the section header size. So this is just the size of this section in bytes, and it's a very simple field. So here I have it highlighted. So we have 01 Alpha Charlie, and that's in hex, and that corresponds to 428 bytes in decimal. So it's saying that this section, the text section, is 428 bytes in size. So the next field is the section header link, and this is just a link to another section header table index. So it's an index to another section header table. So if you look at the struct for our section that we're looking at, the text section, you can see that it's all zeros. So this tells us that there's no links associated with this section. But if we look at the output of readelf that lists all of the section header information, this column right here, this link column, the LK, that is the value that we're talking about. You can see that some of them do have references to other sections. One of them to look at is, like, for example, right here, the link for the sim table links to section 29, and section 29 is the string table. So more than likely, this string table contains the string names, all of the ASCII strings for the symbols in the symbol table. Which table it links to and how it's used will depend on the section itself. But for the text section, there are no links because it's all zeros. And another one that we can look at is the .rel.plt. PLT stands for procedural linkage table, and I plan to go into that in great detail in a later video. But you can see here that it is linked to index 5, and the .rel.dyn or dynamic is also linked to 5. So if we look at 5 here, we can see that that's the dynamic symbol table. And so that means that both of these sections are related in some way to the dynamic symbol section. So the next field we'll look at is the section header info, which is just additional section information. And this just holds special information that depends on the section type. So it can vary depending on what the section is. And again, for our particular section, you can see here that the info is 0, which is verified by the hex binary output. So there's no info associated with the text section. Okay, but again, if you look at the readelf output, you can see that a couple of them have sections right here. Excuse me, they have numbers in the info column. So for this one, the .rel.plt references number 22, and I suspect that that is actually referencing this index 22. The GOT stands for global offset table. So the procedural linkage table and the global offset table are related, very closely related. So my guess is that's what it's referring to. So the next field we'll look at is the section header address align, which is a section alignment value. And so what this does is this specifies an address alignment constraint for this section. So let's look at our text section. So right here we've got a value of 4. Okay, so that means that the section must start on a 4-byte alignment. Okay, and essentially what that means is the address where it's loaded, okay, modulo the address align, which in this case is 4, must equal 0. So in layman's terms, that means that the address must be evenly divisible by 4. That's essentially what it's saying. And so one of the reasons that might stipulate this type of alignment constraint is the size of the largest data type in this section. So in this text section, we can assume that the largest data type is 32 bits because we have a 4-byte alignment. If you look at some of these sections, in this alignment value, if it has a 0 or a 1, then that means there is no alignment. And so we can see here that most of them have a 4-byte alignment, and there's a couple here that have 2-byte alignment, or 1 at least. Okay, so the next field is the section header entry size. And so what this does is specifies the size of each entry if this section is a table. So if the section is a table, then this value specifies the size of each record inside that table. Okay, and so for the text section, we have a entry size right here at 0, and you can see it's confirmed in the hex output. If we look down here, we can see a whole bunch of them that have entry sizes. One thing I'd like to point out is that these are in hex, not decimal. So if we look right here, the symbol table has an entry size of 10, which is 16 bytes. Okay, that hex 10 is 16 bytes. So that means each record inside this table is 16 bytes. And so as you go through, you got 8 bytes, 4 bytes, whatever. So if you see a non-zero value in here, then that is likely each one of those is a table of some kind. Okay, it could also be like an array, but it's basically, you know, an ordered collection of elements that are all the same size is the best way to think about it. Okay, so real quick, I just want to go back to this document here and spend a few minutes on this area right here in the document. If you go down to page 1-15, what this is this is a list of some of the more common sections. So this, you could go through here and read these to get an idea of what some of the more common sections are. So for example, BSS is very common. It stands for block starting segment, I believe, which is like a really old term that basically has lost meaning over the years. But essentially it says, you know, this section holds uninitialized data that contribute to the program's memory image. So this is basically like global variables that are not initialized. And then here you got debug, so debug information. Dynamic is an important one. It holds dynamic linking information. So you'll have this if you do any kind of dynamic linking. So we've got the section header string tab, which we talked about in this video. This section holds the strings for the section names. The string tab, again, like I discussed, it most commonly holds the strings that represent the names associated with symbol table entries. And then the symbol table holds, you know, the symbol table. And the text, again, this is the one that we looked at in this video, and so it just holds executable instructions. So I just thought that was worth pointing out, that this document can help you find some meaning to some of these different sections. Okay, so let's recap what we covered in this video. We described the structure of the ELF section header. We examined each field of the section header in the binary file, comparing the structures and definition in the elf.h, the section header output from readelf, and examined the section header from the compiled binary file in the hex. So that does it for this video. I hope you found it useful, and I'll see you again.